statics. I'm curious now.
It's a statics class. I did have an intruder.
I do statics.
But all the guests were expected.
It was like 5 minutes after class had started. He was just talking. I was like, he makes eye contact. He was like, what are you doing here? I was kind of expecting something to get like thrown at me, but I figured since there's parents and perspectives
Exactly. You gotta be careful.
So,
Keep up the good.
especially because there's parents directly behind me, and if I was mistaken for anything. That's really nice.
If you're gonna do something,
Check your
Unless it's campaigning. Yeah.
10?
Yeah.
take your word for it.
It is. Are you bringing red syrup?
Is that like cough syrup or something?
Is it hydrogen
Yeah, I know it is.
What is that?
Seriously, Colin, what is that?
It's kombucha.
Which is?
Great. That's not like
Fermented tea.
obviously appropriate.
Hey, it's only 12% alcohol.
Well, that's nasty. Like kimchi.
It's really good, actually.
All right.
Yeah.
It's like they're chugging.
Everyone's ready?
Spicy.
We're ready to start. We can talk.
A kick in the pants.
All right, I'll just start. So we've talked about thermal properties, right, through these equilibrium phase diagrams. Today we're going to talk a little bit more about the kinetics. So everything we've talked about on the equilibrium phase diagram is just that. It's the equilibrium. So everything slows very coolly. Cools very slowly.
Where's Blake?
Where's Blake?
He's
He's not here. He's actually going home for the weekend.
He's wide awake.
So he skipped on.
He had to go home for an 80 night. So,
More musical things.
I'm giving him wide berth. Okay. So the equilibrium phase diagrams involve slowly cooling.
Cooling slowly.
So the question is, what happens if we don't slowly cool? Today we're going to talk about kinetics. That is time-dependent phase transformations. And the key here is to recognize that there may be things that phases that exist that are not represented on the equilibrium phase diagram. Because the equilibrium phase diagram is just that. It has equilibrium phases. It does not have all possible phases. In fact, there's the possibility of forming amorphous metals.
Amorphous metals?
Amorphous. You know what amorphous means? No crystal structure at all. It's like glass. Right? Window glass is amorphous. Has no structure, no long-range structure. So you can form amorphous metals if you cool them incredibly quickly. So basically, you take this liquid, which is amorphous, right, has no structure, and just instantaneously solidify it. You'll have an amorphous metal.
Is that stronger then, or weaker?
Well, we'll talk about that later too. But my point is, the phases that exist in the phase diagram are not all the phases. Okay. So in order to do kinetics, we're going to add a third dimension. But because we're trying to write on a two-dimensional board, I'm going to write it, I'm going to draw it in the form of a slice. So this third dimension we call a time, temperature, transformation diagram. Or a TTT diagram. So they describe the phases that are present, the structure that's present, as a function of time and temperature. So instead of, before the equilibrium phase diagram was a function of temperature and composition, right? So we had this. For instance, right? And here we have temperature and composition. what I'm effectively going to be doing now is adding a third dimension of time and taking slices through this.
So transformation is just basically composition.
Transformation is actually phases. It's about what phase is present, not composition. Because the TTT diagram will be done for a single composition.
Okay.
You with me?
So you take a time and a temperature to get a transformation at a specific composition.
Right.
Okay.
So what I'm going to do is I'm essentially going to take a slice like that through the diagram and show what happens as a function of time. Does that make sense? In reality, what I'm actually going to do, I suppose, if you want to apply time is actually in this direction. Right? Because the front face that we've been looking at is the infinite time position. Right? So time is really t equals 0 is back here. You follow me? Okay. So,
God, I think I smell that. It smells like pizza dough or something. I don't know.
You're not supposed to test chemicals
Smells
by
interesting.
smelling them.
Come.
all right.
You're not supposed to test chemicals by smelling them, guys.
Oh, no, that was something else. Oh, gosh.
Oh, apparently I smell myself. I'm sorry.
Apparently you smell like pizza dough.
Okay, so let's take as an example, and this is the reason we're using this as an example because it's probably one of the most important TTT diagrams. I'll do it over here. We're going to take the iron carbon phase diagram, or actually the Fe3C, with the iron cementite phase diagram, and we're going to use a eutectoid composition. Anybody remember what the composition is, what that weight percent carbon is that I'm doing this for?
67, no, that's
0.77.
0.77. Do you have the book in front of you? Did you read that from the book in front of you?
Yes.
Okay. Just want to know whether to be, impressed or not. I appreciate your honesty. Okay. So we're going to take, if you remember, I'm not going to draw the whole thing, but we have the alpha phase over here. Right, and we had the, what's that?
That one? That you drew up over there?
No, this is lead tin, right? Or, that's another one. Right, because iron's got, the delta
Oh, yeah,
here,
that's
right? Okay.
Triple.
So we have alpha here, we have gamma here, and this is 0.77. So we're taking a slice through that piece. Okay? A slice through that thing. And what we end up with is the TTT diagram looks like this.
What is it slicing? Oh, through the eutectoid?
Through the eutectoid, yes. Temperature versus time, and this is actually versus log time. Right, because we want to make sure we can carry things out to infinity. The best way to do that is to put on a log scale so we can bring infinity in close. And this temperature here is the eutectoid temperature. So above the eutectoid temperature, it's all gamma. Now, TTT diagrams assume that we are moving down and to the right. Right? Time is increasing and we are cooling. They do not apply for going upward. Okay, they're only apply for going downward. Okay?
Is there one that applies to going upward?
No.
Okay. You don't really care because once we heat it, it's just liquid.
Right. So, what we get is we get something that looks like this. Whoa.
It's a road.
It's the highway.
This is the 1%.
Highway to life. I walk alone.
Shut up.
Came to a wood. Two roads.
Those are the 1%, 50%, and 100% transformation lines. Because below the eutectic temperature, the eutectoid temperature, right, it's supposed to be all alpha and Fe3C. Right? And what's the structure that we talked about? Do you remember the structure that forms when it goes through here? What's it look like, microstructure?
It's
Straight.
like
Lamella.
lamella.
Lamella. Or lamellar. It's a lamellar structure, right? Most commonly, the lamellar structure does. Okay? So it's going to form a lamellar structure. But if you go fast enough, it stays as gamma. So let's see if I can put these kind of. This is 0, -1, 1, 2, 3.
Oh, Morse goes in counting 4.
You can't take the log of a negative number. You can take the log of a number and get a negative. Right? The log of point, this means 0.1 seconds.
Okay.
The log of 0.1 is -1.
Okay.
This is in, again, t here is in seconds. Okay? So roughly speaking, that's what it looks like. So what that means is, as I quench through here, if I quench the thing fast enough, it can stay gamma. Right? But if I let it go for forever, it eventually undergoes 100% transformation to that lamellar structure. And then what you'll also see here is a specific description of what that microstructure is. I'll explain this in a minute. So coarse pearlite.
TE is the detected temperature, right?
Right. So coarse pearlite just means that it's a lamellar structure. Pearlite is specifically reserved for steel, for the lamellar structure of steel. So coarse pearlite is that. You're cooling it slow enough that it forms thick layers. Fine pearlite then, as you can imagine, has much finer layers. Okay, because now we're cooling fast enough that it's alpha cementite, alpha cementite. It's supposed to be able to form a lot of alpha. Okay, I think I'll form a little cementite, you follow me? Bainite is a material in which the lamellar structure is inconsistent. It is not nicely laid out in parallel paths. Go fast enough, it can't form these nice uniform structures, and so it sort of forms this randomly oriented layers.
So is bainite based off of speed at which you cool it, or the temperature at which you're starting? Because like those are how you have them written there, like one.
They are where you get. So when I the way I use this is that I quench things. So I start out with stuff up here. It doesn't matter. T equals 0. Therefore, infinitely far to the left. Right? Because the log of 0 is infinitely negative. When I cross this boundary, the clock starts when I cross this boundary. So if I could come down and do this, and then cool it down to room temperature, that says that at this point in time, at 1 second, right, I begin forming fine pearlite, and over here at about 10 seconds, I finish forming fine pearlite. I go from 100% transformation to 100% transformation.
Where's the 10 seconds?
Right there. Right, 10 to the 1 is 10.
Okay.
I didn't see that. It's kind of long scale.
Yeah. So you understand? You follow that?
So there's not necessarily a set path that you take
Right.
through this. You use
Right.
whatever you need to get.
Right, exactly. So you can structure the thing the way you want to.
So is it like the top? What? Where?
To your ability to follow that path. Some paths might not be possible.
Go ahead.
Where are each of those perlite and bainite categories? Like where they correspond to?
That section. So right now it's fine perlite. If I'd cooled it down to this temperature and left it for 1,000 seconds, I would form coarse perlite.
What are those? What are these?
Or what?
These.
100% transformation. So in other words, if I did this instead,
Does it not go down to the bottom of the
Then it would
graph?
be 50%.
that would be 50% fine perlite.
50%.
I'll explain the bottom in a little bit.
Okay.
Okay? But at this point, we've 50% fine perlite. Because this stuff over here, the perlite, the coarse perlite, the bainite, that's all alpha plus Fe3C. So in this region, between these two solid lines, I have gamma plus alpha plus Fe3C. I have all three phases coexisting at the same time. Yes?
So, does coarse perlite, does that correspond to the left side, the fine perlite in the middle, and the bainite?
No, top, bottom, top, and bottom.
Okay, is there
So if I
any,
come across here, I form coarse perlite.
Okay.
If I come across here, I form fine perlite. At the bottom, bainite.
But there's no clear delineation between like where one starts and the other ends?
No, because I mean, you can see this is going to be a graduation, right? Just thinner and thinner as we get down here. And then as it gets thinner and thinner, eventually it gets to the point where they're not continuous anymore and they're sort of breaking up into random directions.
Okay, so what are alpha, gamma? What are alpha and gamma? Like, because I thought we were
Alpha
talking about-
iron, right here. Alpha
Oh.
iron and gamma iron.
Okay, so there's alpha. Is alpha not just on the left side there, but also in?
Right, but this region down here is a mixture, right? It's a two-phase mixture of alpha plus Fe3C, which is the right-hand side. Just like this section over here is a mixture of, you know, this is alpha tin, or alpha lead rather. And this was beta tin, and everything in here is a mixture of alpha plus beta, physical mixture.
Right, but it also changes. Even if you stay at the detective point, as you go in, you get into alpha and gamma and combinations and stuff. Is that what you're saying?
Yeah, no, I'm saying this is the infinite point. So you notice if this goes all the way out to infinity, these lines all approach the eutectic. And above the eutectic temperature, it's gamma, or eutectoid temperature, it's gamma. Below the eutectoid temperature, it's, you know, alpha plus Fe3C, or, you know, some kind of perlite, coarse perlite. At infinity, time equals infinity, so I'm doing slow cooling. I have a single transition that happens when I cross that temperature. Does that make sense to everybody? Because all of these asymptotically approach the eutectic temperature. This is only what happens in the very rapid cooling section, which is far away in time from this. I'm basically looking at this plane from the left-hand side. T equals 0 on the far side, this is T equals infinity. Okay. Okay. And this assumes, you know, you like the path that I've drawn here assumes that I basically have an instantaneous quench down to this temperature, and then I leave it at that temperature for this period of time, and then I instantaneously quench it down. That's how the diagram is derived. It assumes I'm moving only downward and to the right. No angles, no kind of curvy lines or whatever. Downward and to the right. Okay.
But technically they are curved lines, because we're talking a log scale.
The red lines.
Well, I mean a log scale, right?
Right, right, but instantaneous is still instantaneous. Right, so downward and to the right still works even on the log scale. There's no straight lines. So, and we can make the approximation that even if my curve actually looks something like this, right? We'd essentially approximate that, you know, we could make some kind of approximation that, well, you know, we got 50% fine perlite. Right, if we went like this, right? I'd say we have 50% fine perlite, and maybe, you know, you have to estimate, right? You don't really have a good way of knowing how much of it is bainite versus how much of it is perlite. So that's why you want to go down and across, so that you can actually understand what's happening to your material.
Does that highway percentage thing come all the way down to the bottom, the x-axis?
I told you, as I just said a minute ago, Josiah asked the same question.
Oh.
I'll get to the bottom in a minute.
Okay, silly goose.
Okay. Now the thing is, all of these phase transformations are based on a diffusion process. You have to diffuse a second phase out of a first phase. Right? So even when the composition stays the same, I have to diffuse an alpha out of a gamma. So alpha will form at the grain boundaries. Remember we talked about with the microstructure problems before, it starts forming at the grain boundaries, the trifold intersections of the grain boundaries. So if I take some gamma that has grain boundaries, and then I cool it, the alpha will begin to form at the intersections of the grain boundaries, and the alpha crystals will grow while the gamma crystals shrink. That's the way the process works. So it's a diffusion-driven process, yes?
Generically, when do we start to see grains starting to form? When, I mean, like around what temperature for?
Well, as soon as it's, from a liquid, as soon as it solidifies, you start seeing grains to form.
So when the film starts to form on the top, if it's cooling in, just that room temperature?
Right, so it's cooling room temperature, grains are forming on top.
Okay.
So if you ever lick your ice cream spoon and then put it back on your ice cream, you'll actually see ice crystals begin to form on your ice cream spoon. It kind of forms dendritically, like little trees. Long stem, and then a stem coming off here and a stem coming off here. You ever do that?
It's funny when you say it that way, but yeah, I get it.
Okay. So that's when you, as soon as it starts to solidify, you see the crystals form. Okay. All right. So these are primarily driven by diffusion. So we got to diffuse the atoms that are trapped in the gamma out to the edges in order for them to transform into alpha. Right? It's a diffusion-driven process. So there are two steps. There's nucleation. That is, we have to start the grain somewhere, like I was talking about with the boiling water last time. Right? You have to have some place for the reaction to start. And then you have growth. That is, you have to get that, once you have a seed, you start building on that seed. So, let's look at nucleation first. We have local diffusion that governs all these atoms have to kind of come together, diffuse through whatever's there to begin with, to nucleate a particle. So they have to coalesce. As I said, things like high energy regions, like in the green boundaries or on the surface, as Colin pointed out, it's going to happen on the surface. You have higher energy on the surface. So there are two driving factors.
Well, this time you guys all have pretty good reason. Yeah, or we didn't play.
Yeah, well,
For nucleation.
Hey Chris, you wanna shut up?
Do you mind?
Are you sure those are drivers and not risks?
Okay, two drivers for nucleation. The first is what I'll call the liquid phase instability, even though it's not necessarily a liquid for the tectoid. Right, just like I was talking about with the boiling water. You superheat the water gets above 100 degrees C, it's unstable. It doesn't want to be water, it wants to be water vapor. Right? The higher the temperature you go, the more instability you get. Right? The second is diffusion to form nuclei. So in this case, liquid phase instability is bigger the colder you get. Right? The colder the liquid becomes, or in this case it could be this would be the gamma, right? But it's gamma phase instability. The colder it gets, the more unstable that material is. Right? That make sense? So if I were to plot it, as a function of temperature, and plot the rate at which it happens, seconds to the -1, a high temperature, let's put T sub E in here, for instance. At the eutectic temperature, there's no instability. Right? At T sub E, there's zero instability, so there's zero rate. But as I get colder and colder, the instability increases. So this is instability. So I get more and more instability the colder the thing gets, the further it gets from the eutectic. As I drop the temperature, I get more and more instability, therefore a higher rate of, or higher likelihood, if you will, of the liquid phase wanting to transform into the solid phase, or the gamma phase wanting to transform into the alpha. Right? The lower the temperature, the more unstable it is. Okay? Does that not make sense?
Well, why aren't we plotting rate on the y and temperature
Simplifying temperature on the y and rate on the x.
Deal with this.
Because over here we plot temperature on the y, so we're going to continue to plot temperature on the y. Right? Diffusion, on the other hand, does not occur very well at low temperatures, right? We've shown the Arrhenius plots. Remember talking about the Arrhenius relationships? Right? The higher the temperature, the greater the diffusion rate. So diffusion does something like that. So at very high temperatures, actually I should make that, let me compress that a little bit so I can get. So at very high temperatures I get lots of diffusion, but I have very little instability because it's very close to where the, to where it wants to be a liquid anyway, or wants to be a gamma anyway. At low temperatures it's very unstable, but I have very little diffusion to drive the process. So what I end up with is I end up with the product of these two, which is the nucleation rate, which looks something like this. N dot, the nucleation rate. Okay? Does that make sense? Yes? Okay. See, it's nice when the back, the back row bobbles their heads, and I know I'm all right. Okay? Actually, more likely to doze off when you're sitting. Anyway, because that's the nucleation rate. Now, that only covers nucleation. What about growth? What's going to drive growth? Temperature, yeah, but how? I mean, what kind of a mechanism do you think growth is going to occur through? Some sort of differential equation. Isn't that the common answer for all engineering problems? Is there a differential equation? Well, it turns out growth is really only diffusion. Right? There's not an instability that drives growth. The only thing that drives growth, once I have a crystal, the only thing that stops it from growing, because it's the stable thing to be in that matrix, right? The alpha is the stable element. There's no instability driving alpha. Once I have an alpha, the only thing keeping me from getting more alpha is diffusing stuff to get there. Right? Diffusing other material to that surface so it can form more alpha. Right? So it's just diffusion. So essentially I end up with adding another diffusion curve to that other one.
To the same diffusion curve?
No, it's a different one.
Okay.
So what I end up with then is I end up with a total thing that looks like this. Something looks like that, where this is nucleation and growth rates. The overall transformation rate, right there in the red. Okay? But I don't really want to plot it as a function of rate. I want to plot it as a function of time. So I have to invert my horizontal axis. And when I invert my horizontal axis, those things become these things. So that hump right there, when I invert my axis to time, becomes this. That make sense? So it's still all driven by the nucleation, or by the diffusion primarily. You know, diffusion really governs, you know, has the biggest impact. But there's still the fact that you have little instability at the top. So the little instability drives this out here. Okay, that's what those are most sort of diffusion-related behaviors that act like this. There are a few that are non-diffusion behaviors. So the bottom of the graph here does indeed end.
What's that nice?
Oh, what are we gonna say?
So you just wrote it up there. I thought you
I'm
were-
still talking here. I didn't
know
walk
if I
out the
said-
door.
Hey.
Anyway, so there are some non-diffusion phase transformations. Non-diffusional phase transforms. The one that we care about here is martensite.
I think that's what MS is.
Martensite start is what it is. Yeah. So we have the martensite start. It's a sudden reorientation of the crystals. So basically, kind of like twinning. Right? Remember twinning? There was like ding, right? And you heard it because it was. So here's the same kind of idea. We have these gamma crystals, and we slam them down cold enough. We slam it down here so it's cold enough. We create such tremendous instability that instead of having to diffuse atoms around to grow crystals of alpha and Fe3C, we spontaneously and suddenly get all of the atoms to rearrange themselves into a different crystal structure, which in this case for steel is martensite. So what you get is and in martensite and steel is a body-centered tetragonal structure. So we're going from an FCC gamma to a body-centered tetragonal BCT structure in martensite. So if you think back to it, right, FCC,
Is that BCT there?
BCT, body-centered tetragonal. All right, so FCC, we've got a atom on every corner, an atom on every face. Right, everybody see that? Right? And if I drew the next atom, next unit cell out, I think that's everything. Okay? 2 FCC unit cells next to each other.
Are the back ones drawn in?
Yeah, back cells don't have dots.
That one does. That one does.
So,
So now, body-centered tetragonal, remember to pick it up. What happens is, you get a slight vertical change in just the vertical dimension of the crystal. And that forms my body-centered tetragonal. Right, so if the vertical dimension were to elongate just slightly, I can't remember, I think it shrinks actually. I'm trying to remember my notes, I think it shrinks. But anyway, the point, that would make sense, it's cool. Anyway, so basically the whole thing shrinks just slightly. So that the original A value is now becomes something slightly smaller and is the new C value of the body-centered tetragonal. So the atoms don't themselves have to move anywhere. They just have to compress themselves together. Everybody kind of see that? How that a body center diagonal could come from this? So basically what that means is FCC is like a body center tetragonal, but with the special condition that the A of the body center tetragonal is equal to the C of the body center tetragonal divided by the square root of 2. If that C changes ever so slightly, it's no longer FCC, it's just body center tetragonal. Okay? So that's how it can happen rapidly. Right? There's just enough cooling pressure to get it to shrink, and then you have a new crystal structure.
So apparently mercury, when it's frozen, and you have a little bar of frozen mercury, if you bend it, it turns.
Really?
Crackles like this.
You also really are really cold because
Yeah, I don't think we'll be doing
I
that.
saw it on YouTube. We could look it up.
Or not.
everything on YouTube
Okay.
is true.
All right, so we end up with this this martensite region. Now, martensite also goes through a series of transformations, just like the pearlite formation. So you have an MS, an M50, which is 50% transformation, an M90, and then, if you go far enough, an M final. But this one is minus 46 degrees C. You go 46 below to get a completely transformed martensite. Okay, so it's not likely to happen. The start is 215 degrees C. This is 160. That's 130 degrees C. So still above the boiling point of water. You get 90% above the boiling point of water. The last 10% requires you to go from 130 down to minus 46.
So basically, we're going to be dealing with things in the MS state.
What's that?
We're working with this material. We're going to be working with it in like the M90 state.
Yes, at best. If you have martensite transformation, you're going to be working with something that's 90 to 95% martensite. However, what's really cool is once you get down into here, the gamma is locked in. You don't get the gamma, you know, if I get down to here and I let it go for a long time, the gamma doesn't change to bainite or anything. The gamma is locked in as gamma. It's room temperature austenite. Okay? So once I get down into here, I don't have to worry about the time anymore. I just got to get myself down into there so that I can lock it, get some martensite to form to lock in the rest of the austenite. And then I can gradually cool it to get the rest of the transformation to occur.
So really all that we need to know, like, I'm just trying to figure out where this graph really comes into play in life.
So we can find out, you know, because we want to know when we quench something, is it coarse pearl, you know, what's it quenching to?
Okay.
We want to know what kind of microstructure we have. Because it turns out, the further I go down this list, the harder the material is. You can imagine, we'll talk about it hardening, but it's going to be a lot easier for dislocation to propagate through a big open space like this than to propagate through this.
So the coarse pearlite, like we get over the coarse pearlite and then we just let it slowly cool after that.
It's going to be fairly soft.
Pearlite?
Right, yeah. There's no driving force to form anything else because it's perfectly at equilibrium with alpha and Fe3C.
And then it'll become martensite.
No, it won't become martensite. Once it's formed alpha plus Fe3C, there's no more martensitic transformation. Martensitic transformation, because alpha is a BCC material.
So those long
It
lines.
only can go from gamma to martensite. It cannot go from alpha or
So those
Fe3C to
martensite lines really shouldn't go past the height.
No, it does, because this only covers down and to the right. Now, I've already gone 100% transformation,
Oh.
right? Once I've gone to that point, I'm done. Once I've crossed the 100% line, I'm done.
So you can't go down to the right and then down again.
I can, but it's not going to change anything. Once I cross that 100% line, I'm done. If I went down, if I did this, and then went down from here, all right, and then went over, then I would have something that's 50% fine pearlite and 50% martensite.
Okay.
Even if I went to the 90% line.
So once you past that 100% line, you're done.
You're done, right?
Once you pass
Is
the
that enough
50% line.
You're done with that 50%, right?
Okay.
Does that make sense?
Ish.
Okay. And this is, though this is true for the eutectoid composition, you can also do a similar thing for a hyper or hypo-eutectoid. So this is, what the eutectoid composition would look like. But if it's hyper or hypo-eutectoid, depending on where I am, right? So if I'm coming down here instead, this is T, call it T sub S, that would be T sub S. Okay? There's a similar knee in the curve, even for a hypo or hyper-eutectoid. So here I still have gamma, here I have gamma plus alpha, here I have gamma plus alpha plus Fe3C, here I have just alpha plus Fe3C. That makes sense to everybody?
And as we go into that alpha, that gamma plus alpha section, it would be a like different concentration of gamma plus alpha, getting more and more alpha as we go that way.
No, the amount of alpha is, this is just a percent transformation. And generally we only draw the top, where you start the transformation. So like, as I go across here to the right, I'm converting more of my gamma to alpha, but I'm never going to get any more alpha than I'm supposed to have in my system, right? It's the inverse lever rule that tells me how much alpha,
Okay.
right? So the amount of alpha will never be more than what it's supposed to be.
Yeah, but like the farther you go this way,
The more complete that
alpha
reaction
will
is,
be, but it will never exceed the amount
Right,
it's
right,
supposed
right.
to. Okay.
Okay, any questions? Okay. Then, let me, I think we've covered enough. I think we've got a, do I want to do that? Yeah, let's do this one. No, let's not do that one. We'll do that one next. Is that? Let's do this one.
You can give us a gift.
What's that?
You can give us a gift.
No. Okay, you guys want to figure that out on your own?
No. That's true.
Well then. All right, so even though the earlier section we talked about, this thing talks about crystal nucleation, as I said, it also applies to solid state transformation. Right, so gamma to alpha. So here we have equation 10.1. I've written out equation 10.1 in the slide. Can be used to describe the rate of precipitation upon cooling of a supersaturated phase in a 10 weight percent tin, 40 weight percent lead alloy. All right, so we go back, we're back to the lead tin diagram. Probably should have put the lead tin diagram up there. Hopefully by this point you guys are pretty familiar with this. This is 19, this is 97.5, this is 61.9, and well, the temperatures we're going to have to deal with. Okay. Given precipitation rates of, my superscripts didn't stick. Okay. 3.7 times 10 to the third per second, and 1.4 times 10 to the third per second at 20 degrees and 0 degrees. Okay, so the rate at which precipitation occurs. Everybody understand that? Okay, so we're at a 10, 10, 90, right? We're doing this. So we're coming down this graph. The graph right here. Okay. So we basically take this and we're cooling it down. So we're moving into this two-phase region where the alpha lead is breaking into alpha plus beta. And we're precipitating out beta. Right? So it requires that the beta, the tin atoms diffuse together to the grain boundaries, particularly, in order to form the material. So we have precipitation rates of 3.7 times 10 to the third. So the precipitation rate, the growth, this is the growth rate. Precipitation rate is 3.77 times 10 to the third at T equals 20 degrees C. And the precipitation rate is 1.40 times 10 to the third at T equals 0 degrees C. Right? Everybody follow that? And they're asking to calculate the activation energy for this process. So what is it they're asking for? In my diagram, in my equation there, what is it they're asking for?
Q.
They're asking for Q, the energy necessary to cause a precipitation event. So I'm supposed to solve for Q. So how would I solve for Q?
Divide C over L on each side.
Divide what?
Divide C over. Divide the whole thing by 10. So look at the.
Just a reminder, this is not, that's not, we've done this once before with diffusion. Okay, we want to solve for Q. What do we do? Take a ratio.
Oh.
Remember? So we have P20 and P0. So what we really want is we want the ratio of P20 divided by P0 so that the C's cancel out. Right? And that's going to be e to the minus Q over RT20, which is R times 293, divided by e to the minus Q over RT2.
So P is G?
P dot is the precipitation rate. That's the equation. It says, although section 10.1 concentrates on crystal nucleation and growth, so that's a growth rate,
Okay.
similar kinetics laws apply to solid state transformations. So growth rate and precipitation rate have similar functions. Basically they're saying they're both Arrhenius behaviors.
That makes sense.
Okay? Both precipitation and growth are Arrhenius behaviors. So we can take the ratio of those two. Right? So that's e to the minus q over r times 1 over T2 minus 1 over T1. Right? So we get rid of the C and we can solve for Q because we know R and T. And we're out of time, so it's fine. We're not going to get through that.
What's R?
What do you mean what's R?
What's R?
R is the universal gas constant. Oh, in this case, yeah. In this case, it's 8.31. You know, it's R bar from thermodynamics is R here. Good. R. Okay. So hopefully you can then you take the log of both sides. So basically we end up with the ln of P20 over P0 times R divided by 1 over T2 minus 1 over T1 is equal to Q. Actually, do the algebra. All right. Thank you for coming. It's been wonderful having you all.
Good. Still. Not going anywhere for one open body this time. Little class and everything.
Oh yeah,
Experience.
experience the
Magic.
The wackiness. That's pretty fascinating.